good afternoon. I hope you're now all refreshed with a cup of coffee. I'll be talking about the optimal vehicle electrification level in a battery-constrained future. This study was done by Concawe in 2020 and 21, and the main authors were Eshan Shafiai, Marta Hugo, and Roland Dauphin. The context is fairly clear. There is the EU ambition to accelerate the electrification of road transport, in particular light duty, and at the same time becoming a global leader in sustainable battery production by developing its own local European production capacity. Now, there are large uncertainties associated with that, and I'm not going in detail here because we get a very detailed presentation later on by Rémi Conubert. So basically, the main issues is, will we really be able to ramp up fast enough batteries, number one, and number two, it was said already today in various presentations, have we got enough raw materials in order to produce the batteries? When the study was started, we did a forecast and we looked in the literature what the forecast on production capacity in the EU is for 2030, and we've seen extreme ranges between 0.3 terawatt hours per year and 0.95 terawatt hours per year. Now the situation today, now we're in 23, and the latest data I've got is that the global battery capacity deployed is 1.42 terawatt hours per year, out of which only 0.163 terawatt hours per year are installed in Europe. So the assumption that we might have difficulties having enough battery is most likely a reasonable one for the next 10 years. Now, what are the objectives of that study? We basically want to investigate and answer the following key questions. First and foremost, how do we make the best use of a given certain level of battery supply to minimize greenhouse gas emissions of EU-wide newly registered cars towards 2030? Now, if we want to do that, we need to shift from a back-to-back comparison, basically comparing the performance of a BEV versus a PHEV in terms of emissions, to a systemic approach if we're short of batteries. So in other words, putting the question of feasibility at the core of the issue. Do we have enough batteries? And if not, how do we allocate them so that we get the maximum benefit in terms of reducing greenhouse gas emissions? And the third point, important point, we think is we need to start the mitigation of the transport-related greenhouse gas emissions now, literally, without waiting for the full rollout of the gigafactories, which will take some time, as we all know. The second important question in such a scenario is there a role for PHEVs? And if so, how much does the utility factor, which is defined as the percentage of electric drive divided by the complete mileage in percent? Okay. Let me illustrate that the objective again on a simple comparison here. Let's assume we want to minimize the well-to-wheel CO2 emissions of 10 new passenger cars. And we've got only 100 kilowatt hours of battery capacity available to do that. So illustrates here two paths. We go on the left side, so we allocate to two BEV vehicles 50 kilowatt each, using up all our capacity, and the remaining 8 vehicles will have to be ICE vehicles. So sales composition is 20% electrified, and the electrified mileage is then 20%. Now if we go the other path and we allocate to 10 PHEV vehicles, 10 batteries, 10 kilowatt hours each, we've got PHEV only, but since the PHEV we assume a 40% electric drive, we get an electrified mileage of 40% in that scenario. Now, that clearly shows that depending on the systemic constraint that we face, allocating batteries to PHEVs can first of all maximize the share of electric drive and thereby minimizing the well-to-wheel CO2 emissions. So really the purpose of that work is to allocate the batteries to BEVs, PHEVs or HEVs in such a manner that the well-to-wheel CO2 emissions will be minimized, and we do that for a range of battery constraints, basically. A quick word about modeling approach. So it's been done in two steps, essentially. A linear programming model was set up, which does the optimization of the vehicle mix to minimize the greenhouse gas emissions under the various constraints, but always assuming a fixed battery size for the various electrified powertrains in that mix. And in a second step, we did introduce a second variable, which is basically the battery size of the PF. If you do that, the maths get a bit more complicated. You get a nonlinear system. You need to update the framework, but that has been done. And then you can do essentially the same, but you don't need to consider fixed battery sizes anymore. Here, the key assumptions that we made in the study. The battery supply cap ranges between 0 and 1.2 terawatt hours per year. The annual sales have been assumed to be, in the base case, 16 million passenger cars per year. The annual mileage, 12,000 kilometers per vehicle per year. And FCEVs are not taken into account in the passenger car fleet mix because they are too small. They don't play a real role. What we did allow is the full EV penetration scenario, which means assuming that the max share of 100% of the new sales can be PF and BEV in 2030. Now let's have a first look at the first results here. So the optimization in this case has been done for 3 different utility factors, 20, 40 and 90. The diagrams basically show on the y-axis the share in passenger car sales mix in percentage. The various powertrains are shown by different colors, and on the right-hand side you can see the emissions from that fleet with the well-to-wheel emissions. These are depicted by the green squares. Yeah. So let's have a look at the utility factor of 20 first. So what you see is, first of all, ICE engines or ICE powertrains only play a role for the trivial case when we do not have any batteries. For all others, it's simply a mix between BEV and HEV in this scenario. So the larger the battery supply cap gets, the more BEV comes into play and plays a larger role. If you do the same for the utility factor of 40, what you see a market difference here. You see the orange bars coming in, which represent the PF, and they actually present a quite sizable chunk of the mix over a large range of caps, as you can see here. If you go to the utility factor of 90 in the calculations, the first important thing to notice is the change doesn't really, the mix doesn't really change anymore. So from 40 to 90, the amount of the different vehicles in it is more or less constant, but what does change is the well-to-wheel emissions. They are considerably lower, so the gradient for making progress here is a lot steeper with the higher utility factor. I'd like to point out, so obviously if you go from 20 to 40 in small steps, you arrive at the break-even point, which is in our case 30% when the first PFs come into the mix. It's not in the diagram here, but it will play an important role. I'll come back to that later. Okay, here we've made a slightly different approach. We've chosen 5 sets of pairs of powertrain combinations which have minimized in the same manner for the various battery caps, and the emissions are shown on the y-axis. What you can see here, first of all, if you look at the blue one, BEV plus ICE combination, that's essentially the worst under all conditions, except for caps above 0.55, PHEV plus HEV combination, and PF plus ICE seems to be better in terms of, or worse I should say, in terms of well-to-wheel emissions. but that's somehow artificial, since by then, if we use that combinations at some point at 0.2, we're in saturation and we've got only PHEV, so the further capacity will not be used in the mix. BEV plus HEV basically is the red curve, is the optimum over a large amount if the utility factor is small, as I've showed previously. And the important curve here is the green area below, which allows the optimal mix of all powertrains in here. And it's varied between 30%, that's the upper limit, bordering to the red curve, and the bottom, I'm not gonna do it. And the lower one, which gives the best greenhouse gas emission results. Maybe a slight comment: for very small battery caps, PHEV plus HEV combination is effective if we only consider 2 powertrains. Okay, optimization of sales mix for various BEV battery sizes and various utility factors. Let's talk about utility factors first. There is the WLTP utility factor, which is based on the worldwide harmonized light-duty vehicle test procedure, and is used for CO2 calculations and fuel economy calculations in the homologation. So it plays a critical role here. And if you compare that, that's the blue curve in here in the diagram, and it's plotted as a function of the electric range of the PHEV in kilometers. And if you compare that to the green curve, which is representation of what you find in real world when you use your PHEV as normal customer, what you see here, you're roughly by a factor 2 smaller in real world with these factors than in the WLTP. Okay, now let's look at, with that in mind, let's look at the results here. Let's start with the real world utility factor. So if you increase in that row the battery size from BEV 200 kilometers reach to BEV 600, if you go down that road, what you see is you get more PHEV into the system, basically. So the PHEV plays a larger role. The bigger the BEV battery, the more PHEVs we'll have in the optimized mix. And the other important message, again, if you look at the same on the WLTP utility factor, again, the mix is very similar if you compare it left to right versus real world, but you see a dramatic improvement again, as previously, on the well-to-wheel greenhouse gas emissions. Okay, now since the utilities factor plays such an important role, let's look at them under real-world conditions using the simulations that have just been described by Joris Melgar from EFPN. They've developed that tool, and it's shown here as a function of the battery capacity in kilowatt hours and as a function of the frequency of charging. So the various colors in the chart represent different recharging frequencies. Now, if we look at the first example, if we do a 15 kilowatt battery, recharge it every day, we arrive at a 77% efficiency for the utility factor. If we look at 10 kilowatt hour battery capacity of our PHEV and do recharging only every 2 days, we're down to 48. On 5 kilowatt, recharged every 5 days, so if we're lazy customers, or we decrease further down to 28%. Now let's stick with the 5 kilowatt battery and go back upwards again. In other words, if we go from 5 days on that small battery to every day, the utility factor increases again back up to 44%, and if we are very ambitious and we recharge twice a day, we arrive at 63% of utility factor, which basically means, and that is an important message here, increasing the charging frequency on PHEVs is a very efficient way to increase the utility factor under real-world conditions, since that's what matters in the end. and it helps us, as has been shown, a lot in reducing the greenhouse gases. Okay, and finally, let's look at the break-even utility factor I've mentioned. Again, that is the factor when PHEVs, above that, PHEVs do play a role in the mix for various battery sizes of PHEVs and BEVs. So we've chosen here 5 PHEV sizes, ranging from PHEV 20 kilometer, could have gone back. From 20 to 40 to 60 and 80 and 100, and we combine that with a change in the BEV batteries from 200 to 600. The numbers are always kilometer range, basically. So you've got, for the PHEV 20, you've got 5 utility factors depending on the size of the BEV, and shown in blue here. And if you move on for the various colors, you always get 5 different utility factors per PHEV. Now, increasing the battery size of PHEV, so if we go in that direction, you see that we increase the break-even utility factor. If we increase the battery size of BEVs, so we look just at the battery size of the utility factor, it goes the other way. Then the break-even utility factor of the PHEV decreases. This trend is most pronounced for the larger PHEV sizes of 80 and 100 kilometer range. Now we compare this to the real-world utility factors that I've just described, which we get from the chart from IFPN as a function of usage and battery size for the various combinations of PHEV and BEVs. Now, you see here that step function in brown. If the utility factor calculated once per day for the various PHEVs here is a step function, and the important message here is it's always bigger than the break-even utility factor, no matter what the combination of sizes of batteries on PHEV and BEV are. If we introduce now the case when we do recharge only every 2 days, the yellow step function curve for the various PHEV, we're still above, in all cases, above the values for the break-even. And only if we go to recharging five days, it starts that for larger PHEV battery sizes, in particular 60, 80 and 90, we start to get, for the smaller BEV sizes, we get utility factors, real-world utility factors, which are higher than the real-world utility factor. So, what does that mean? That basically means that the lower-range PHEVs should be used in the optimal sales mix under battery-constrained condition. First of all, to make the best use of the limited battery resources, but also what we've just seen, it's always a safe bet. We will always have a PHEV which works well in the mix. Okay, conclusions. I'd just like to point out the 2 main messages from my perspective. So, because we talk about the battery supply and demand in more detail later, on the optimal electrification level, basically, PHEVs would be the main component of the optimal sales mix towards 2030, even under conservative or real-world utility factors. And secondly, what is also important, recharging more frequently increases dramatically the real-world performance of our utility factor and thereby minimizing the greenhouse gas emissions in the fleet. With that, I've got 27 seconds left. I thank you for your attention.